Um, Thanks for joining me. My name is Kishore Reddypalli. I work at GE Digital. I lead a product called Operations Optimization. It is being built on the Predix platform. I will go deeper into it, like what is Predix and all that. So today I'm gonna walk you through, like, introduce you to some industrial, like true industrial use case, especially like in a GE power energy kind of sector. And I'm gonna go over like how we have leveraged the big data ecosystem, especially Spark and the Hadoop Yarn cluster, to analyze the data that is coming in. And I'm gonna talk about an in-house optimization framework that we have built that runs in Spark cluster. And also, I'm going to briefly walk you through some of the streaming and batch-related analysis that we do for a few of our use cases. And then I'll share some of the challenges that we have encountered and some of the performance metrics. Then we can take some Q&A. So before we dig deeper into the conversation, like, what is GE's mission? So if you, I think like most of you are familiar with like GE light bulbs, but GE also manufacture these huge equipments like jet engines, steam turbine, gas turbine, drilling equipment. So GE is all over across different sectors like oil and gas, power, wind. So there are a variety of equipments that they manufacture. And the life of those equipments like varies from machinery to machinery, but like it's a longer life. It's not like a mobile phone like with a 2-year thing. So we need to have like some way to monitor the health of those equipments and provide a better service to the customers. So to do that, so GE has been investing a lot in the digital sector. So as part of that, these are some of the areas that they want to do, like improve the asset reliability and the availability of these equipments, and monitor the mission critical events. Like if there is any issue with the equipment, like we want to alert the operator or the field engineer so that they can take necessary decisions. And that is one part, like that is more of like what is happening, just let the operator know. But we also want to optimize the performance so that like we can leverage some of the machine learning and artificial intelligence technologies so that we can go gather the data and understand like what is happening and how is being operated, and we can make the necessary suggestions saying that like if you operate this way, you may be getting better outcomes of it. So those are the things that we want to monitor and provide a better service to the customers. So on that note, so I picked one of the use cases. Like there are n different use cases, which we typically call it as an industrial internet. But the one of the use case in power plant is, in the power sector is heat rate. So heat rate is something like the amount of fuel that is consumed to generate like a unit of electricity. So this is a very important piece, like to measure the power plant efficiency. So if you ask like how is my power plant doing, like how much, what is the performance of it? So there are various things that they measure, like emissions, the fuel costs, etc. But they're all tied with, at some point, to this heat rate. So how does the heat rate constitute? So the heat rate is like we have to monitor the fuel that is being consumed every time, like when you actually start a steam turbine, a turbo machinery, and see like how much power, how much energy it is being generated. So those are all different, very important factors. And I'll just touch upon on the data volume also. So in the aviation industry, like when a jet engine is in a cruise mode, like when it is in the air, like there will be like hundreds and thousands of data points that will be generating by the sensors that are attached to this jet engine. So we want to collect the data so that we can, we can predict there is something going to happen, like with the machinery, there will be some maintenance. so that we can schedule it by the time that the flight gets landed. The same thing, like I think like this morning, Joe was giving in the keynote speak that like an end-to-end connectivity of like scheduling for the maintenance, ordering for the parts, and making it everything ready so that the downtime of that particular fleet is reduced. So in the same context, in the context of power, like, it's the same thing, like, you have like thousands of data points that are being generated by these sensors attached to those turbo machineries. And what we want to do is we want to collect all the data into like a cloud environment and analyze the data so that we can bring in some insights and provide some intelligence to the customer so that they can take necessary decisions. So for all that, GE has built something called Predix platform. Just to get a pulse, like, have you heard of Predix platform before? Okay, not bad. So, thank you. So Predix is like more of an industrial platform that runs in various cloud providers. We also have our in-house cloud data center too, but so Predix has 3 different pillars, I would say, like where one is edge, like that is where the actual equipment was installed and it is running in an active state and it generates the data. And the other part is like more of a cloud where we collect all the data and we run our analysis, etc. And it has bootstrapped with a bunch of technical technologies like Hadoop, etc. And eventually, like, we want to enable the users to visualize it. We visualize what is happening. We want to connect to the data and see the recommendations, etc. So the apps are going to be running, is also running on the cloud. But so this is at a bigger picture. This is the end-to-end portfolio of the Predix platform, and it is with the security. So with that, like, if I get into from the big data ecosystem perspective, so on the very left-hand side, like, you have the data collectors, which is nothing but the edge play, like where you have a bunch of sensors. So there will be some OSMs, if you're familiar with the terminology. It's the on-site monitoring devices, which actually collects the data. And it gets pumped into our cloud-based service, which is called Event Hub. It's a gRPC-based messaging channel. And it gets the data into the cloud. And these components, the visualization app component is the one which will enable the users to deploy the analytics and have the apps to visualize the data outcomes of it. And we have like a microservices-based architecture where we have these services running in a PaaS platform called Cloud Foundry. And these services will enable to deploy them into the cluster. So for deploying into this, the Spark runtime cluster, which is powered by Hadoop Yarn, we need to have a way to have a REST API to actually deploy these jobs and all that. So for that, like, we leverage the Spark job server to deploy our jobs that are being submitted from the user activity. The same thing, like, we have enabled something called data providers, which we're going to talk about those in a minute. But these data providers will help to actually get the necessary data for those analytics that are being deployed and being running in the Spark cluster. So I'm going to dig deeper into each of these boxes. Like, we have an ability to do stream analysis and batch analysis in a seamless fashion and in the Spark cluster. And we also leverage we heavily leverage the time series data format because majority of our data relies on either asset and the time series because of the majority of the sensors. And there are other financial data aspects too, but majority of the data is Predix the time series data. So getting into the Spark, so we we have the Spark as our analytic runtime engine. Like, I mean, by this time, like you all know, like the value proposition and the value that it adds to this ecosystem. But how do we use that? How are we using the Spark cluster in our ecosystem? So primarily, I would say that, like, from our application standpoint, especially in the production from an enterprise perspective, we need to have like a REST API so that, like, it's not like a background job that we deploy an analytic and be running. Like, we want to deploy the analytic from a user-driven, from an on-demand based. So from our application standpoint, we will have an app that internally actually gets, have an analytic that gets executed through those REST API, and those jobs will be submitted to this cluster using the job server that is running. And it is secured, and it is multi-tenant, so that we can distribute it and support for multiple tenants. And the optimization framework is the library that runs, like I mentioned, it runs in the Spark cluster. And we heavily use the Spark SQL and Spark streaming as of today. So what is the need of this optimization framework, especially in the enterprise world, providing that as a platform? So we want to standardize our analytics that are being deployed and being authored by different data scientists so that we can bring in consistency across our ecosystem. So for doing that, like, we have built this framework, and also we want to abstract the complexity involved, like, to dealing with the collecting the data and processing the data and all that. So for that, we build this framework, and it primarily offers us a simple API which enables the users to interact with the data frames. So it's all built with Spark DataFrames based architecture. So it has an API which the user can write a simple analytic so that they can use the APIs that we provide and get hold of the data frames. The same way, we have defined our own schema, like, which is, we call it as industrial data frame schema, which I'm going to show you in a minute. It's a flattened data structure, like, instead of nested data structure from the time series data or the asset data. And we have the data providers, which is an ability, when you write an analytic, it includes like an inputs, bunch of inputs. You have a computation logic, and you produce some output. But your inputs may be coming from variety of data sources. Like, maybe your data will be sitting in a HDFS, or your data is sitting in a REST service, or your data is in S3. So you want to go and collect the data. But we don't want the data scientists to worry about the complexity of where the data is coming from and all that. They only rely on, like, this is the data frame that I'm expecting, and I want to deploy that analytic, and I want to write my own logic. So with that, like, they can just concentrate and spend time on their own logic or the algorithm. And when they deploy it, when we operationalize it, we know that for this particular tenant, for this analytic, it requires the data, and this is where the tenant's data is. So we have that all intelligence built into this framework. And in addition to that, like, we have parallelism. So it is smart enough to actually, when it collects the data, how to partition it and how to better leverage the cluster based on the data points that were fetched. And we also want to make that simplified. Like, from a user standpoint, they may want to run their analytic, their logic, for every data point that is coming in from the sensor to detect it, or they may want to do like a batch analytics, so they can just say that I want to run this analytic in this mode, so that we can go and collect the data and in a batch mode to collect the data and run the analysis. So, and also we enable like UDFs, so that like they can do aggregations, interpolations, and unit of measure conversions. So this is all being interactive from the user standpoint. So under the hood, these the data will be converted into like the request will be converted into a sequence. So this is how it will look like from an optimization framework architecture standpoint. So if you see this, sorry, I'm bad at this one. So this is like a simple library that runs inside the Spark. This is like something, an analytic that in the context of heat rate, I want to measure how much fuel has been generated, how much fuel has been consumed by this particular equipment, and use that as an input for predicting in future how much degradation can happen from that equipment perspective, because over a period of time, if the fuel consumption is more, and if the maintenance cycles the operators are maintaining in a certain fashion, if we have an analytic which can determine and say that if the field operations are happening this way, obviously there can be a potential degradation in the efficiency of your equipment. So if I bake all that concept into an analytic or a chain of analytics, I can go ahead and, when I go ahead and deploy it, I need an ability to collect the data. The first thing is for collecting the data here, like I mentioned, the data scientists or the data engineers, they write the analytic, but this framework knows that okay, this analytic is being deployed and it needs the data of time series data of these sensors, from these sensors. So when the data is coming in, the analytic gets triggered and being executed because it's all configured by that. And coming back to this framework, like I mentioned, they will be using an API which will interact with give me my time series data frame so that I can run my logic on the data frames and what are the different sensor data that I'm interested in. The same way, under the hood, it has the data frames architecture where when it collects the data from these data sources, it will convert those into a data frame and hand the data frame to the analytic. So under the hood, like I mentioned, it has the data tenant configurations, schemas associated with this one. So going into the data providers, which in other words, like the data connectors, you have a file-based data connector, you may tell that my data is always coming from the HDFS, or you may tell that my data is in an external service hosted in a different cloud. I want to go and collect the data at whenever this analytic is being executed, go get the data and give me that as a data frame. And Spark comes with some of the data connectors like the Cassandra and Postgres, but we will tenantize that and make it available. And we have, like I mentioned, we have variety of messaging pipelines that we want to listen to, which is the Kafka, Kinesis, and Event Hub based on the cloud provider where we are in. So Event Hub is something that is built in-house, which is a gRPC-based messaging channel. So if you look at so these tags are nothing but in a general term, we call it as it's nothing but a sensor. If you have a temperature sensor, we call it as a tag, and there can be multiple tags coming from an equipment in a single payload. They may collect the data and send the data through OSMs from the edge. So here, if you see this for the data, it defines from what is the quality of the data, what is the value, and what is the timestamp when it was observed. So what we do is we register this schema in the Spark framework as part of this optimization framework. So that runs in the Spark library, Spark framework. So this particular data is actually coming from let's say a REST service. So that data will be flattened out using based on that schema that is there, and it finally gives the data frame. If you are familiar with, this is a Spark data frame, not Pandas data frame, but so it looks like a relational table which has flattened data, which the tag and what are the observations that were made over a period of time, so that the user can just at runtime, the respective SQL gets executed on that on this data frame. So the same way, for the asset model also. So typically, when we write an analytic to analyze the data, for example, if there is a customer who has a plant, who has multiple plants across the sites, and they have built an algorithm to measure the performance of a steam turbine or some gas turbine of certain model, and they want to run the same algorithm across the suite of assets that are available in their plant, they can just deploy that analytic And that analytic can say that, like, you know what, I want to run this analytic for this asset. These are the variety of assets that I want to run against. So the same way, we have our own asset model to define, like, okay, this asset has, these are the equipment, these are the sensors that will be part of this particular asset. And so that, like, we can look up for what are the sensors that are needed so that, like, we can go and pull the data from the time series store. So the same way, like, we have a flattened schema registered with this optimization framework so that the asset model data frame can also come as a flattened data structure. So it was a little conglomerated, but I want to show you this, the sample analytic. If you see this, the users who are writing these analytics in this framework will not be worried about, like, creating the Spark context session, etc. So here they will be writing the logic of assuming that they will get a data frame of asset and the time series data frame, and they can author their own SQLs, like they can plug in their SQLs and run with it. So it is a completely an abstracted format, like where the users will just write the logic, they can offline test it out, and they can productionize it, they can deploy it into the cloud environment. So with the real data, it gets executed. Here, if you notice that, like, there is an asset data frame and there is an input data frame, time series input data frame, on which they will, majority of the time, they write the SQLs. So there are some certain use cases where they may require, like, in addition to the time series, they may require other data sets too, so they can register their providers and do that. So getting into the actual stream processing, like I mentioned, for anomaly detections, for quality of the availability of these assets, etc., they need to monitor the data that is incoming data that is coming in, and send some notifications to the users if it is some mission critical events. Like, so in this case, like, from the flow standpoint, like, the data collectors are nothing but on the edge, on the OSM side, like, they collect the data and they send the data to this event hub channel. And we have a way these data providers, like I mentioned, as part of the optimization framework, will register with the channel pipeline, and it can actually collect the data and make the data available to this analytic. And this is a stream-based analytic, so it will be running in continuous mode. And this runtime gateway is nothing but our the REST interface through our applications, how it got deployed. And once the stream processing has been done, it will produce the results to our messaging channel, and eventually it will be streamed to our applications for visualization purpose. So the stream processing, like, I think I don't have to touch more upon the microbatch, but, like, those who are not familiar, microbatch is like, instead of, like, continuous data, like, you will get the batch of data in chunks with whatever the value that was configured in Spark. And it is a continuous application, so it will be running in continuous mode. And it has the support for multiple stream sources. The optimization framework actually can listen to multiple streams. And it is tenant-aware data pipeline, so it knows that, like, which pipeline to register for this tenant. And the context-based data pipeline is, like, there will be a variety of data that is coming in. It's not just time series. It may be some other data events that may be coming, so that we can reduce the noise of the data. And obviously we have the window-based slicing capability with that to calculate the moving averages over a period of time, how it is performing relatively. So some of the pointers, especially in the industrial world, like the challenges that we encounter is the microbatch interval. So majority of the use cases are good enough to fit in the microbatch interval. Like, it's not like a nanosecond kind of thing that is required for, especially in our case, at least for some of the use cases we are dealing with as of today. And the other thing is the data congestion. So when the data is coming in, like, there is some things that we have encountered with the Spark is, there might be some reasons, like maybe we have not configured in an efficient way with the number of executors or the cores in the Spark cluster. And if the in-stream data that is getting from Kafka maybe if we don't pick it up, the Kafka or Event Hub or like these messaging pipelines actually host the data for a certain time. And if it is not configured efficiently, we may encounter like a loss of data. So, and the other one is the delayed data. So especially because this is coming in batches, and if your analytic that was deployed expects like certain tags, and in the batch those tags data is not available, obviously the logic that gets executed on the data is not with quality because it may not have the enough data to provide a good insight into the for the outcomes. So the delayed data is a big challenge. Like if the tag 1 data has come in one batch and tag 2 data didn't came in the same batch, then like your analytic may not be able to execute efficiently. So these are some of the challenges or the things that we have encountered. So on the other hand, like from the batch processing standpoint, when the analytic gets executed, again, like these are the different data sources where the data can be collected. But the significance of this framework is like to actually go and collect the data, to actually process the data in a parallel fashion based on the number of data points that were observed. At the same time, like it has a bunch of aggregations that we need to do, like if we want to do some kind of unit of measure conversion based on the user preferences. So all this will be done through this framework with this with the UDF capabilities. So again, the partition of data, etc. And we enable our end users to use Zeppelin as the workbench kind of thing, where they can go ahead and author the analytics with the time series data and all. So we are in the process of enabling our data sets to be like an interpreter so that they can collect the data, and which is very friendly so that they can play with the data sets. So these are, again, like just to reiterate on those challenges, like, in the stream processing, the data arrival. So we are looking at like SPA2.x with structure streaming so that we can increase the delay, so that we will have a way to capture the data, wait for some more time, like when enough data points are not available. And the state persistence. This is another thing where like we want to have like a chain of analytics so that one analytics results needs to be used for the other analytic for in an intermediate state. Like how we want to do it. Like we are looking at SPA2.x and other like a caching mechanisms. And like I mentioned, we have an in-house data messaging channel, like which is the event hub. For that, like we have written a gRPC-based receiver, like the Spark receiver, which can go and collect the data with the gRPC servers. But like as part of that, one of the challenge that we encounter is because of the Guava jar that is being used by Cassandra connector and Spark, and gRPC uses a different version. And at the bottom line, it's Java, so multiple versions gave us a huge challenge for us. So one of the options that we have opted for like is a shading, which will actually package that whole thing together, but there are some downsides too for that one. I'm open to if you have any suggestions, if you have encountered such problems in the Spark. And the performance tuning. So this is another thing that we have noticed, which I'll show the metrics. So when we are writing this optimization framework, like this, how we partition the data and all, if we are not cognizant enough to leverage some of the Scala's APIs, the data structures, like using the concurrent-based data structures, you will not be truly leveraging the cluster in an efficient fashion. I'll show you the metrics, like how much performance improvement we made, like once we started using those data structures. And Yarn client mode is another limitations. So I recommend like always go to the cluster mode. But so one of the challenge is like the distribution of jars. Because of the shading, like the jars that are needed at runtime to get executed, it became like so huge, the Uber jar. It takes so much time to actually distribute that when you actually submit an analytic, it actually distributes to all the executors. the distribution of the jars that gets copied on the number of nodes or the executors that you have, like, increases if it has if it is too huge. So that is the biggest challenge that we had from a latency. And loading from HDFS, like, there are some challenges to load those jars, like to pre-distribute it to the HDFS in the client mode. You won't be able to do it because from the HDFS as such. With AWS, there is an EFS file storage where you can put those jars into it. So there is a workaround there. But here we encountered some latency-related issues. So this is an example of the sharing plugin that we have used for the gRPC connector, so that, like, it will, it's a Maven-based. It packages that whole jar into a different package name and gets deployed, so that it will avoid the versioning conflicts in the JVM. So if you noticed, so these are this is a batch mode analytic that was deployed, and these are the metrics where, if you see this blue line, and which says that, like, the amount of time it took actually for processing the batch data, like, given an analytic, you want to go and get the data for this time range and analyze the data. So this is before that code changes that I was talking about, like, where for the Scala concurrent related APIs that we didn't use. And once we used it, like, it knows efficiently how to distribute it and how to parallelize the data and how to use the cores of the processors in an efficient manner. So at the same time, like, this is a slide where talks about number of data points ingested in the stream mode and how much time that we have taken to actually process the data points. We have seen, like, this like, it all depends on the use case end of the day, and how the analytic has been written and how the logic has been written, and the number of tasks that gets created under the hood in the Spark as part of the DAG execution. You need to go and fine-tune for the number of executors or the number of cores that you have configured. It's not necessarily that, like, you will get better performance if you just increase the number of executors or the number of cores. You need to go back and tune it and see, like, how the number of tasks are being distributed. So it all depends on the use case to use case. So, and excuse me, from the production standpoint, we use Grafana for monitoring of the whole ecosystem, which it's a one single location dashboard that we use for the resource usage from the Spark and from Kafka, etc., or the Event Hub. So, so next steps, like, so we are looking at moving to Spark 2.x streaming, and we have done we have touched on the surface of the Spark cluster, but, like, we are looking at how we can leverage machine learning pipelines, and we are also looking at how to integrating with the TensorFlow for our artificial intelligence and the deep learning use cases. And like I mentioned, Zeppelin as a service is going to be the workbench to enable the data scientists to author the analytics and operationalize the analytics into the Predix into the platform, and enable the data providers as a service, so that you may have the data that is sitting in like a weather data from an anemometer or an NWS weather station that you want to go and collect the data. You can just write a simple data provider to deploy it into it, so that the framework knows that, like, to enable that to get the data at runtime and provide to the analytic. So with that, I can take some questions, but I just want to stress that, like, if this is something very interesting for you guys, we are hiring for especially the big data engineers in various levels, but feel free to talk to me. Yes. It's actually, the question is the job server. It's a Spark job server. It's not Livy. It's an open source that was there for a while. It was contributed by Oyala company, but you can, the name itself is called Spark Job Server. Yes?
So when you mentioned Spark job, is that kind of job running on the YARN? So is that a scheduled job when user deployed to the Spark server, or it's like one-time job?
It depends on it. Like, if you take the job, let's say like you wrote a logic and you deployed the job, and you have scheduled it to run like every 1 hour, then you are actually running in batch mode. It creates a Java application, the app process, and it will terminate it, and again after 1 hour, it actually again submits the job and all that. But whereas in the stream mode, it's a continuous application, so that it will just stays in the memory. Your process is not dead. It is still live and it's in continuous mode.
So those jobs basically write the data to the data frame in the Spark?
Sorry?
So basically those jobs generate the data to the data frames in the Spark?
Yes, so those jobs requires the data. Like one aspect is your logic is running in, you wrote a logic which says if this is greater than 200, just write something. But to measure that, like you need to provide the data to that particular logic. So this framework actually goes and collects the data, converts that into a data frame, and make it available to that analytic.
So where is the raw data stored?
So the raw data can be in HDFS, or it can be in a REST API, like a Postgres database or a Cassandra database. So that data will be read and it will be converted into a data frame.
And that is flowing via your event hub?
Yes, if it is in a stream, if it is a stream data, it will be continuously flowing through the event hub. But if the data is at rest, so if it's like large data sets, then it will be running in a batch mode to collect the data from like a Cassandra database or something.
So how you basically trick the POS executors at you trick the POS executors, those kind of Spark configures at a job level, or it's basically the global?
So as of, that's a very good question. So as of today, it is still at the global configuration, but we want to get to the point where like based on the job based or like based on the tenant based, we want to go and dynamically tune it. So as of today, it is global configuration. It's under the hood. So. Any other questions?
You mentioned registering schemas a couple of times. What do you use for registering?
Sorry, like?
You mentioned registering schemas.
Oh, registering schemas. It's not like we are using any kind of metadata services kind of thing. It's just a, if you look at like to bring in any new data provider in the Spark framework, it's just like a rudimentary way of registering your schema definition in Scala. So it's a very native way. It's not like any third-party service that we are using.
Does it do an automatic discovery of the service?
You actually register your schema with a key. So yes, Spark actually provides that spec. So you can register that and you can look up with that key. Okay, thank you. Thanks a lot, guys.